Good day, everybody. My name is Afolabi once more, and I'm here for another physics class. And in our previous videos, we have started up refraction of lights, and today we'll try to see how we can complete the knowledge of refraction and move into something more interesting. Now, before now, I have defined what refraction is for you as what change in velocity of a wave when it is moving from one medium to another. So basically what causes refraction is when a wave moves from one medium to another, and that is refraction. And I also discussed what Snell's law is, and I told you what Snell's law governs is used to calculate the refractive index when wave is moving from one medium to another in terms of the sine of the incidence angle and sine of the reflected angle. We also talk about the triangular prism, where we got the refractive index of the triangular prism in terms of the angle of deviation and the angle in the triangular prism. All these videos have been done before now. If you by any chance miss them, you can go to download them or watch them again. We also talk about the refractive index in terms of the real depth and apparent depth. The real depth is the actual depth of the object in the new medium, while the apparent depth is where you see the object to be in the medium. So the real depth and apparent depth can also be used to calculate the refractive index of the material. I've also talked about the total internal reflection, where you have a ray of light moving from dense medium to a less dense medium, but instead of refraction to occur, what happens? We have reflection of the light back into the original medium. Now, this will only occur when the angle of incidence is more than the critical angle, which is the maximum allowable angle for refraction to occur in medium 2. So it is possible you have light traveling from one medium to another, and that ray of light, instead of refracting, will reflect back to the original medium. And that only occurs when the angle of incidence is more than the critical angle. The last part of the refraction we are going to talk about, refraction of light we are going to talk about, is the application of refraction of light. What are the applications of refraction of light in our daily lives? One of the basic applications is in the periscope. Periscope. I know you still remember what we call a periscope, and a periscope is something you use to view over an obstacle. Okay, instruments used to view over an obstacle. Now recall that when we're dealing with plane mirrors, we said we can use plane mirrors for periscope. Likewise, we can also use triangular prisms as periscope. Okay, so triangular prisms can be used as periscopes. Okay, and how do we use triangular prism as periscope? We use that one of the angle 45 degrees. We have that prism this way. We have the prism this way. This is a prism. And here we have another prism. We'll make sure that the angle is 45 degrees. Okay, use a triangular prism. Make sure the angle is 45 degrees. Okay, and this is your eye. Okay, so if you have an obstacle, this is the obstacle. So by the time you view through here, what happens? By the time you view through here, what happens? What you get so you have a view over the obstacle. And that is one thing you can use your periscope to do. You can use to view over an obstacle. This is the obstacle, and you view over the obstacle by using a periscope. Now, another application of total internal reflection is the optical fiber communication. Optical fiber communication. And what's an optical fiber? An optical fiber is a glass material. Okay, a glass material that is drawn into wire. A glass material drawn in wire for satellite communication, satellite or high speed communication. So when you have an optical fiber, let's say this is a wire, an optical fiber, you incidence light into the optical fiber at a critical angle, at an angle greater than the critical angle. And what do you see? You see the ray of light reflecting throughout the optical fiber. Light travels very, very fast. The speed of light is around 3 times 10 to the power 8 meters per second. So if you are able to transmit a signal at that speed, through a fiber, then definitely that signal will be a very high speed signal. The third application of total internal reflection is in the formation of mirage. Formation of mirage. What is a mirage? A mirage is a kind of optical illusion that is formed whenever there is a temperature difference in the atmosphere. Okay? Whenever you have the atmosphere and a layer is formed where you have a cold air and a hot air, definitely you have light moving away from the denser medium towards the colder medium. Why? Because the cold medium is a dense medium, while the hot region is a less dense medium. So if you have light traveling from the less dense medium, which is the cold region, once it's about to enter into the hot region, what happens? It will go back into the cold region, forming a fake image of the object, which we call the mirage. So basically, the formation of mirage is due to what? An illusion. It is not real. And a mirage is a fake image that is formed by changes in temperature of the environment. So basically, those are the applications of total internal reflection. One is in periscope, where you can see the triangular prism arranged at angle 45, such that light can easily view over an obstacle this way. Then you can also have optical fiber communication, where you have information to be transferred at high speed, and you have the angle of incidence of the light at an angle greater than the critical angle, and such that the information will be very, very fast. Then you also have formation of mirage, which I told you is formed due to what? Due to temperature difference. You have a fake image due to temperature difference. Now, all these are applications of refraction. But one of the greatest applications of refraction is noticed in a device known as lens or lenses. Okay? And a lens is a kind of glass where you have refraction of light giving you new images. So when we say lens, or rather lenses are transparent glass with high refractive ability. So when you have light moving through a lens, the light will refract. And what I simply mean by refract, I mean change in speed. The same definition for refraction you have here is what you have under lenses. So when light passes through lens, the direction of the light will change. Of course, we have so many types of lenses. The types of lenses, we have the convex lens, and we have the concave lens. Okay? The convex lens is the convergent lens, which has this format. This is the convergent lens. And the reason why we call it convergent lens is that any ray of light moving towards the convergent lens will do what? Will converge. You can see they converge. Any ray of light coming through the lens, they refract by what? By converging. They all refract by what? By converging. So we call it a convergent lens. You can see the refraction coming on here. This is light coming from a particular source. And when the light got to the lens, what happened? They all refracted. That is, they changed the direction towards a certain point. Now that point is known as the principal focus. Does that ring a bell? Yeah, it's ringing a bell, because the principal focus is also something we see under mirrors. Introducing us to a concept that the concept of lenses is somehow synonymous with the concept of mirror. Now let's check this other type of lens. The other type of lens is the divergent lens. The divergent lens diverges light that passes through it. Look at it. This is a divergent lens. This is a divergent lens or a concave lens. Any ray of light passing through a divergent lens diverges away. You can see any ray of light diverges away. Any ray of light diverges away, and any ray of light diverges away. So these ones are diverging or concave lens. Any ray of light that hits the lens will refract by what? By diverging. But here, any ray of light that hits the lens will refract by what? By converging. Of course, we have so many other types of convex lens. We have the plano-convex lens. This is plano-convex, and we also have the plano-concave. We have the plano-concave lens. This plano-concave. Why do we call it plano-convex? We call it plano-convex because one side of it is plane, while the other side is convex. This one side is plane, while the other side is convex. Now, we have talked about the types and what lenses are. We are going to talk about the mode of operation, which I've already started talking about here. That for convex lens, what happens? The ray of light, they converge at the point. But for concave lens, the ray of light, they diverge at that point. Now, as I told you the other time, we noticed some kind of analogy between lenses and mirror. That shows us that lenses basically, they would have some synonymous character with mirrors. Basically, your lenses behave like mirror. Lenses behave like mirrors. But not just ordinary mirrors. The paradox here is that your concave lens, convex lens behave directly like concave mirror. Concave mirror. They have the same property. This is your convex lens behaving the same way with your concave mirror. They behave the same way. That is, both of them are what? Both of them are converging. What do I mean by they are converging? Any ray of light that comes to them, what happens? It will converge. Any ray of light that comes to them, it will do what? It will converge. So the only difference there is that the image of a lens is formed after the lens, while the image of this mirror is formed in front of the mirror. We also have the concave lens. The concave lens behaves the same way as the convex mirror. The concave lens behaves the same way as the convex mirror. This is the concave lens. Is diverging. Okay? This is the convex mirror. The convex mirror is diverging. Is diverging. Any ray of light parallel to the principal axis will diverge. Here, any ray of light parallel to the principal axis will diverge. So both of them are what? Diverging. So it is very, very important that you understand this analysis before we go on. That when it comes to lenses, your convex lens is converging, while your concave mirror is converging. When it comes to lenses, your concave lens is diverging, while your convex mirror is diverging. Concave mirrors can be used in describing lenses. One of the terms we use in describing lenses is the optical center. Optical center. Optical center. And it is somehow synonymous with the pole of a mirror. The optical center of a lens is the center of the lens, where every ray of light appears undeviated after refraction. The center of the lens. Center of lens. Where every ray of light appears undeviated after refraction. They are not deviated after refraction. Okay, every ray of light that passes through the optical center for convex mirror, this is the optical center O, that's the optical center, okay? So every ray of light passing through that place will not refract. Then for concave, this is the optical center O. So the optical center of a lens is simply the center of the lens, where every ray of light passing through that point will not be refracted. We have more terms like the principal axis. We are not new to that. The principal axis is a parallel line to the horizontal. A parallel line to the horizontal passing through the optical center. A parallel line, the horizontal line through the optical center. Optical center. So that horizontal line, okay, it could be this. This is this line here, passing through the optical center is what we call the principal axis. Of course, we also have the principal focus. All these things were also defined when we were dealing with mirror. And the principal focus is what? The points, just like mirror, the points where every ray of light will appear after what? Refraction through the lens. The points on principal axis, where every ray of light appear, every ray of light parallel to the principal axis, every ray of light parallel to principal axis will appear after refraction. So that point where any ray of light, for example, if you have a ray of light parallel to this principal axis, okay, it will pass through what we call the principal focus after refraction. And that is what I just defined here. Any ray of light parallel to the principal axis after refraction will pass through the principal focus of the lens. And the focal length F is the distance between the principal focus and the optical center. Distance between principal focus, the distance between principal focus and optical center. Okay, so I will leave you to define the other two. But remember, I told you the definition is not difficult. All you need to do is to remember the same definition we gave for mirror and just change some key terms and change it to the definition of that lenses. We have center of curvature. Center of curvature on assignments. What is center of curvature? Okay, then the second one. Is the radius of curvature. Radius of curvature. Both of them, center of curvature and radius of curvature. Of course, you know that the radius of curvature, when we're dealing with mirror, the radius of curvature of R was 2f. It's still valid here. That is 2 times the principal focus will give you the radius of 2 times the focal length will give you the radius of curvature. And the center of curvature, of course, is twice of the principal focus. So you know how to define those two for me before the next video. So in the next video we'll be talking about, we'll be looking at the calculations involved in lenses. 2 things. Number 1, the calculations involved in lenses. Number 2, how they form their images. Remember, we discussed how mirrors form their images. Okay? For this type of mirror, remember, the nature of the image depends on what? The position of the object from the mirror. But for this type of mirror, the nature of the image is always the same. It's always diminished, erect, and what? And virtual. Okay? But for these ones too, we have the nature of their images, which we are going to discuss in the next video. Don't forget to ask us questions and download much more of our videos. Thank you.